So we're going to finish up with Newton's universal law of gravitation today. Tomorrow we're going to look at something which is very closely related to gravitational forces, but it's not a gravitational force. It's called a gravitational field. And we're going to have to be very careful starting tomorrow to make sure that we don't confuse the word field with force. Although they're connected and they're related to each other, they're as different as the temperature of the barbecue and the flavor of the cheeseburger. They're just different things, okay? They may be connected. You might need the temperature on the barbecue to get the cheeseburger, but those two things are different ideas. This is Newton's universal law of gravitation. The force of gravity between any two masses is g times the first mass times the second mass over r squared. That g is a capital G, and it is called the universal gravitational constant. Not to be confused with lowercase g, which is what we're going to talk about tomorrow in more detail. Lowercase g happens to be near the surface of the Earth 9.81 newtons per kilogram. Capital G on the surface of the Earth is that number. It's on the screen. Capital G on the moon is that number. Capital G in outer space is that number. This is what's called a universal gravitational constant, as opposed to that little g of 9.81, which we can sometimes call a local. Are you with us, Alex? Which we can sometimes call as opposed to little g 9.81 newtons per kilogram, which we sometimes call a local gravitational constant. But it's a totally different type of constant. Anyway, that's how you calculate the force of gravity between two masses. I guess one other thing before we go over any questions you have. R here is the distance between the masses, and that's what we will usually say, just the distance between the masses. But what we really mean is the distance between the centers of the masses. And sometimes you have to, if you're dealing with celestial bodies, you have to add the radius of the planet or the radius of the object. Sometimes you don't. It depends on the situation. Finally, I believe on your formula sheet that they probably have a vector symbol above Fg. And they also have it in absolute value signs. This goes back almost to day one of this course. When we leave out the vector symbol, we're saying it's the magnitude of the force of gravity in this case. I could put the vector symbol plus the absolute value brackets to mean the same thing, but I typically don't. So can you please take a look over your work? Does anybody have any questions? Go ahead, Jay. Okay, so let's all take a look at number 6, please. And by the way, before we look at number 6, if you look at number 1, the answer to number 1 is very, very tiny. When you have two students that are sitting next to each other, there is a gravitational force attracting them, but it's certainly not big enough to overcome any frictional forces holding them to the floor, right? If friction didn't exist in any way, it would be an interesting world because all of the objects would be continually being pulled towards each other. So number 6. Two objects, each with a mass of 200 kilograms, produce a gravitational force between them, and then you're asked for the distance between them. And I'm glad you asked about this question. We've got two masses. There's something about this that we haven't really talked about yet in terms of Newton's universal law of gravitation. First of all, when you're asked what is the distance between them, we're assuming it means the distance from center to center. So what we're trying to find is this distance here. And I think you're okay with the idea of what it is we're trying to find. When you're told, and we have the masses, I guess I can put the masses in 200 kilograms. 200 kilograms. You're told that the gravitational force, quote, between them, whatever that means, which I'm about to explain, is 3.7 times 10 to the negative 6 newtons. What that means is that there is a force due to gravity that is pulling this mass to the left, and the force due to gravity is pulling this mass to the right, and the force is 3.7 times 10 to the negative 6 newtons. It's almost, not almost, it is Newton's third law, that these two objects are forcing each other. So we talked a little bit about this the other day. When I figure out that there's a force due to gravity acting on me 600 newtons towards the center of the Earth, I'm being pulled towards the Earth with that force. But the Earth is also being pulled towards me with that force. It's just that we tend to think of the object and not the Earth. So I don't want you to look at this question and think, well, maybe we have to take this force and cut it in half because there's a force on each one, or maybe we have to double it to find a total force. That is the force of gravity. Newton's universal law of gravitation says F sub g equals g m1 m2 over r squared. What's going to happen here? We're going to get the force due to gravity of 3.7 times 10 to the negative 6 newtons. This is equal to g, which I'm just going to abbreviate as g. We know it's 6.67 times 10 to the negative 11. And we know there are a special set of units there that make this all work. And I don't really have room to write out 200 kilograms times 200 kilograms, but that's okay because I can do this. When I multiply two things together that are equal, that's the same as just squaring them. And this is over r squared. So how is it we go about solving this? I'm not going to talk about cross multiplication here. I don't think it's necessary. I might in a minute. The idea is mathematically, and this is a very important notion in physics, that when you're trying to solve for an unknown that's on the bottom, that's not good. And I will take it even further and say to you, and if you have me for Math 20-1, how many of you have me for Math 20-1 next semester? Okay. So if you have me for Math 20-1 next semester and presumably 30-1 next year, I make a big deal out of the fact that fractions are not our friends. Like, we don't like fractions. We would rather not have fractions. So mathematically, what you do to this, and I've painted myself into a corner here, so I'm going to move it here. Mathematically, what you do to this is you say, I do not like that denominator. So to get rid of it, I'm going to multiply both sides by that. That's a math approach. I'm eliminating a denominator because then it's easier. And if you have me as a math teacher, and if you had me as a math teacher, you'll remember this. My philosophy in math is to take any math problem and make it into an easier problem. Take a grade 12 problem, turn it into a grade 11 problem. Then turn it into a grade 6 problem, and we're done. So this becomes a simpler problem because now I have r squared times this number. And because I'm talking about the rearranging in the math here, Jay, I'm not really interested in the units. Okay? And this is equal to g times the 200 squared. So what happened here was by multiplying both sides of the equation by the same thing, I've kept the truthness of that equation. It's still valid. Okay? Because you're allowed to mathematically, and I'm just debating whether I want to get into a big discussion of this. When you have an equation, as long as you perform the same operation on both sides, it's still valid. I can divide both sides by 10. I can square both sides. I can take a logarithm of both sides, whatever that is, you don't know yet. So now what I have is that, and now I can divide by this number to get r squared. So I'm going to end up with r squared equals g times that 200 squared over that force of 3.7 times 10 to the negative 6. And we'll finish this, and then I want to talk about the mathematics of rearranging it in a different way. Because as much as I say, oh, that's physics and this is math, we do need to know how to do the math, right? I mean, you have to. So let's calculate the answer first. I need to take the universal gravitational constant. I need to multiply by the 200. I need to multiply by the 200. That's m times m. I just chose to enter it that way as opposed to going 200 squared. It doesn't really matter. And then I need to divide by that 3.7 times 10 to the negative 6. Did I get that number right? 3.7 times 10 to the negative 6? That's what it is in the question. So what this is giving me is r squared. So r squared is equal to 0.72. And that means r in this problem will be the principal square root. If you're wondering what I mean by principal square root, it's because in Math 20 you will learn when you take the square root, you should really go plus or minus. We talked about that in the first unit when you find VF. But in this case, r is a distance, right? It can't be negative. So we take the square root to get r, and that should be the answer. So about 0.85 meters, and that's what it has for an answer. Are we okay with that, Jay? Okay. I don't know where I got this idea. I suspect it was from maybe a junior high math teacher I had along the way. When you have something like this, notice how I write it, by the way. I want to copy this. I want to show something to you. That if I take a look at this thing that I have written, and I go back to the beginning where I said Newton's universal law of gravitation. This is a math idea that if you have me for a math teacher, I'm very finicky about stuff like this. It's different in how I've written it. And I don't know if you see it, but the difference is if I want to express FG as a fraction, I can do that and the fractions are lined up, right? Now, when you see stuff in print, it's not written that way. So if you had a problem in math that was 12 equals 4 over x, it's likely to appear in print like that. However, I always say, write things so that the fractions line up, even though there's no fraction. So, for goodness sake, and I don't know if some of you are doing this, you may be, when it comes to equations and mathematical statements, just stay away from writing stuff like that. That's okay for units, like meters per second, but when it comes to numbers and equations and mathematical statements, that's a bad idea. Anyway, I think it was Mr. Glover, my grade 8 math teacher, said that if you have two fractions that are equal to each other, and there's nothing else of substance, it's not plus pi or anything else, it's just a fraction equal to a fraction. There are two tunnels connecting each side of this. And the tunnels go from the top of one side to the bottom of the other. And things are allowed to travel along the tunnels. So since x is in a denominator, I don't want it in a denominator, I want it in a numerator. That x tunnels its way this way and goes up here. The 12 is in the way, so the 12 has to tunnel its way back down. And that's how you would get the answer. So it's a visual kind of thing, and when we take a look at number 6 here, if I start off with Newton's universal law of gravitation, and I didn't consciously write it this way, but it just happened, right? There is a denominator and a numerator. I can just swap these two and get r squared equals g mm over the force. And you really need to get used to doing that. It's like speed equals distance over time. How do I know time is distance over speed so quickly? I swap the v and the t. So it's a useful kind of thing. Anyway, I think I've answered your question. Any other questions? Yeah. Okay, let's look at number 5. Gravitational force between two objects, and you're given the distance. The mass of one object is given, and you're given the force. What is the mass of the other? So let's call this M1. So what we have is we have R is 0.21 meters. We often see stuff like that in science, 2.1 times 10 to the negative 1. That's 0.21. Okay. The gravitational force is given. The mass of the first object is given, 55 kilograms. G is known. I'm not going to write down what it is. Just put a check mark beside it. We know what it is. And we want to find M2. I don't really know that we need an itemized list because it's pretty obvious which formula we're going to use, right? We're going to use this formula. The gravitational force equals G M1 M2. So this is what I mean. I'm writing G M1 M2 on the same line as F. I'm not doing this or anything else. And this is over R squared. So I'm going to highlight for us what we want to find. And I know that when we first start off in Physics 20, particularly in the first unit, you want to put the numbers in first and then rearrange. Would you agree? I hope that you're going to see from this example, and maybe you've already discovered it, putting the numbers in because the numbers are so big sometimes and there's so much to them may actually be confusing in terms of rearranging. If I want to get M2 by itself, it's already on the top, which is what I always want for an unknown. That means I have to get rid of all this other stuff, which means since I'm dividing by R squared, I have to multiply by R squared. I'm dividing my unknown by R squared, so I have to multiply to undo it. Since I'm multiplying my unknown by G and M1, I have to divide them. And if you stop and think about it, that's that tunneling thing, isn't it? That's saying I need to take this R squared and move it up here, and I need to take the GM1 and move it down there. You could certainly cross-multiply. If you cross-multiply, I'll come back to the solution in a second, but if I take this formula, which is over 1, equals G M1 M2 over R squared, and I cross-multiply, that means I write the top times the bottom equals the top times the bottom. You okay with that? And then say, well, how do I get M2 by itself? Well, I have to divide by GM1. I have to divide by G, and I have to divide by M1. So I end up with M2 equals F, the force of gravity, times the distance squared over the universal constant and also over M1. So that's the setup. Now what we have to do is put some numbers in. I'm going to just write these numbers down. 3.2 times 10 to the negative 6 times R, don't forget to square R, 0.21 squared, over G, which I'm just going to abbreviate as G, and also over M1, which is 55. Maybe I shouldn't do that. You know, I'm going to write out what G is. Don't worry about why I changed my mind. Briefly, I changed my mind because I didn't want you to look at this and see G and think it's an unknown. It's a number we know. This is equal to M2. So let's talk about your calculator, because it's a real shame for you to get questions wrong on assignments and exams and quizzes simply because you're not using your calculator properly. Okay. So when I enter 3.2 multiplied by 10 to the negative 6, and don't forget what that means. That means if I took 3.2 and I moved the decimal six places to the left. It's 0.000032. Okay. And I multiply by 0.21 squared. And now I have to divide by that. Okay. We have time, and we're not in a vacuum here always talking about physics. I'm a math teacher. I want to make sure you understand something. I would like everybody, so we're going to take a break here. I would like everybody to take 30 divided by, I don't know, 5 pi. I want you on your calculator to figure out what 30 divided by 5 pi is. And I suspect that many of you got about 18.84. Is that right? Yeah. That's wrong. So if you got 18.84, you're not realizing something. You're realizing that when you enter, and I'll show you that calculation, which is wrong. 30 divided by 5 pi, 18.84. That is wrong. Because what you have entered is 30. You went divided by 5, and then you went pi, which means times pi. Well, your calculator is going to take 30 divided by 5 and times that by pi, which is not what we wanted. We didn't want to divide only by 5. We wanted to divide by 5 pi. And there's two ways out of this little problem. One is to go 30 divided by brackets 5 pi. How many of you got the right answer? How many did it that way? Okay. How many of you got the right answer in a different way? You did, Lamise, probably what I do. And I just say to myself, I have to take 30 and I have to divide by 5. And I got to divide by pi. Or did you calculate 5 pi first? So you can also calculate 5 pi first. I just like to do this. And now let's go back to reality here with this question. If you take a look up here, I'm going to have to divide by g and m. I have to divide by g and I have to divide by m. So that's my thinking when I enter this in my calculator. Sahara, where was I? 3.2 times 10 to the negative 6 times 0.21 squared. What I do is I go divided by capital G and divided by 55. That's what I do. I'm not a big lover of brackets. I think brackets can be overdone. Like I've seen students enter this and they put brackets around everything. They go bracket 3.2 times 10 to the negative 6 and bracket times bracket. I need the brackets around nothing there. Okay. This is the answer then. That's the second mass. If you wanted to, you could certainly do this. If you wanted to, you could do, well, that's not right. Because I have the brackets, I don't want divided. Okay. If you wanted to, you could do what Lamise might do, which is to multiply the g and the mass of 55 first and then go top divided by your answer. You could do it that way. Anyway, is that helpful? Okay, good. Any other questions before we get started today on the new material? Yeah. 11? Okay. So this kind of question will be on your exam next week. But this kind of question is not a big deal in this course overall. Okay? There might be one multiple choice question like this. The idea behind this, in terms of me teaching it to you, is so that when you get to Physics 30, and we do this with a lot of different situations in electricity and magnetism and nuclear physics, you know what to do. Would you agree that that's Newton's universal law of gravitation? I've just spaced things out because I want to talk about what those variables do to produce the gravitational force. But that's it. And I've also on the bottom, instead of writing r squared, wrote r times r. Okay, a little math lesson. And again, we've done this before, but it bears repeating. This is not a simple idea. Okay? If I were to take a look at the fraction, I'm going to call it f for fraction, 4 over 11. That has a certain value, right? If I were to take a look at the fraction of 4 over 22, that has a different value. Okay? Is there a relationship between these two fractions? Well, we could calculate them. 4 divided by 11 is this number. 4 divided by 22, 4 divided by 22 is this number. Now, I don't know if you can tell. I picked numbers that aren't really obvious, but they're pretty obvious. This is equal to 0.3636 etc. This is equal to 0.181818, etc. Right? Is there a relationship? Well, yeah, this second fraction is half as great as the first fraction. Okay? And the lesson to be learned here is that when the bottom of a fraction gets bigger, the whole fraction gets smaller. And more specifically, I multiplied the bottom of this fraction by 2. Right? It went from 11 to 22. When I double the denominator of a fraction, I cut the entire fraction in half. And you might even see that by going back to junior high math and recognizing that 4 over 22 is 1/2 times 4 over 11. It's 1/2 as great. So when I make the bottom of a fraction bigger, the whole fraction gets smaller. If I double the bottom, the whole fraction becomes 1/2 as great. What happens if I were to go instead, totally different question, if I were to go instead from 4 over 11 and I go to 8 over 11. So I've doubled the top now of this fraction. What happens to the whole fraction? Well, we already know what 4 over 11 is, but I'm going to recalculate it. 4 divided by 11 is that number. What's 8 divided by 11? 8 divided by 11 is this number, which is twice as great. So when we double the top becomes twice as great. And really looking over here, let's talk about the m's now. Since these masses are on the top, whatever happens to the masses will happen to the force. If I double one of those masses, the top of that fraction becomes twice as great. So the whole fraction, which is the force, becomes twice as great. Okay? And let's not worry about the question yet. If I were to double r, think very carefully about this. And I'm not asking you to shout out an answer. I'm asking you to think in your own brain personally about this. If I were to double r in this formula, am I doubling the bottom of the fraction? If I doubled r, does the bottom of this fraction get doubled? Alex? No. It does it twice, right? So it gets doubled and doubled. It gets multiplied by 4. So if I were to double, you can see that I put a 2 here, but I'd put a 2 there, I'm really quadrupling the denominator. So the fraction would become 1/4 as great. If I were to triple the distance, then what happens is the fraction becomes 1/9 as great. And let's not lose sight of the fact that the fraction is the force we're after here, right? Okay. So with all of that in mind, and this is not, what we're doing here is not something you would do on a written response. Okay. In Physics 30, I would talk about how you would demonstrate this. But we're just looking at the equation, and we're saying, let's see. What is the new gravitational force? So we know what the original force is. If the masses are both doubled, well, that means that I have to put a 2 in front of this and a 2 in front of that. And since I'm multiplying the top of the fraction by 2 and by 2, the whole fraction will become 2 times 2 times greater. So if this original fraction was this number, which it was, and I doubled both masses, if I take that force and multiply it by 4, I'd get the new force. If those were the only changes that were made. They're not though, right? The other thing that's happening is you're tripling. And really think of it this way. And I'm verging on now explaining to you how you would put it on paper. But all of this that I'm going to highlight, that's this. That's that original force before we put numbers in. So then what I'm saying is, if you take that original force and multiply it by 2, and multiply it by 2, and divide it by 3, and divide it by 3, you'll get the answer. Or we could say I'm going to take the original force and multiply it by 2, and multiply it by 2, and divide it by 3 squared. And this is why we call this the inverse square law. If we triple r, then the opposite, inverse of tripling, is dividing by 3, but you divide by 3 squared because it's the inverse squared law. So just to finish this question, and then we'll get started with today's lesson, we're going to take that original force, which is the original fraction of 3.24 times 10 to the negative 7. We have to multiply by 2 twice, which means multiply by 4. By the way, here, you understand that these two 2's don't have to be the same number. I could say that one of the masses is doubled and the other is multiplied by 5, in which case we would have a 2 and a 5 on the top. The only reason they're both 2's is because it says both masses are doubled. And by the way, if it said one of the masses was divided by 2, then you could put a half on the top. Now we have to divide by 3 squared. I'm just going to do it this way. I could have very easily entered 9. Or I could have said divided by 3, divided by 3. Is that, for everybody, is that helping out? Because I know we did these before, but it takes a while to get mastery in these types of questions. All right, so as we move forward here, everyone, I am going under an assumption, and I mentioned this yesterday, that if I give you 2 masses in the distance, you can find the gravitational force. Like that. Like not that quick, but it's really just a matter of putting the numbers into your calculator. Okay? All right, so let's move on. Today what we're going to look at is, it's just called Newton's Universal Law of Gravitation Part 2. We're going to continue to apply that formula. So what we're dealing with here is, and this diagram is not drawn to scale. Okay? There's so many things wrong with it. I pulled this from your textbook. First of all, if you take a look at the 2 distances and you compare this distance that I'm going to highlight in yellow to this distance in blue, the distance in yellow, and I'm just doing a rough approximation, the distance in yellow is about 500 times bigger. Okay? Approximately, not exactly. So if I were to draw this to scale, the distance between the moon and the Earth is very, very small. In reality, and I feel as though this is important, I don't want to just hand wave away this diagram. Whoops. In reality, if this is the Earth, this is the moon, and this is the sun. Okay, and that's not even drawn to scale, but it's better, certainly better. So not only are the distances all askew, not well drawn, but the sizes of these objects are considerably off as well. But that's okay. You're given in this diagram the mass of the moon, the mass of the Earth, the mass of the sun. The mass of the sun it's hard to even imagine what this is, like how big it is. I'll talk maybe a little bit later about how large that is. If you are in North America, it's not really working out. You are on a boat at the equator during this eclipse. What will happen is, actually this is a lunar eclipse, I got to change that. If you were an astronaut here on the moon, this is a lunar eclipse. I hope it says lunar eclipse. It does. Okay. It's not an eclipse that we would observe on Earth. Then you wouldn't be able to see the sun. The sun is blocked out by the Earth. And on the moon, there would be a big circular shadow. That's what a lunar eclipse is. The question is this. At this point in time, what's the net gravitational force exerted on the moon by the Earth and the sun? So you need to understand something before we go on. Gravity doesn't care if there's objects between them. So when I look at the fact that this book is pulled towards the Earth, right? I don't take this book and hold it over the table and expect that the table blocks the gravitational force of attraction between the book and the Earth. We know this from a very early age, that if you drop this, it still falls, right? So gravity cannot be blocked. And the word net, when you look at net gravitational force means total. So if we want to determine the total gravitational force acting on the moon, we have to calculate the gravitational force acting on the moon because of its attraction to the Earth, and we have to calculate the gravitational force acting on the moon because of its attraction to the sun. Now, I don't know which one is bigger, but this is going to be your first task. This will be the force of gravity between the moon and the Earth. This will be the force of gravity between the moon and the sun. So, it doesn't matter which one. Let's do the sun first. Think about this for a second. Don't just, if you are already calculating, make sure you get the right answer, for goodness sake. But I don't want you to miss something. That when you use G, mass of the moon, mass of the sun, over r squared, r is going to be this distance. It's the distance between the centers of the two objects. So we have to add these two highlighted distances together in our calculation. So we're going to have G, mass of the moon, mass of the sun. Can I just stop us in our thought process here? Are you okay with me not writing the numbers in? They're right there. We can see them. Over, we're going to have 3.84 times 10 to the 8 meters plus 1.5 times 10 to the 11 meters. And that's what we're going to have to square. And you will need brackets there for that. So do me a favor, please. Calculate that force due to gravity. Alex, you were pretty quick on the draw there. You think you have it? You'll have to read that to me. I can't see that far.
So for the sun, 6.67 e to the negative 11. That's 1.99 e to...
What I'm asking, though, is what do you get for an answer?
4.3 e20.
4.3 times 10 to the 20. Yeah, and that's fine. By the way, if you ever write that, even though it says E20, you don't write E20, you write what I've written. But before we go on, does anybody else get that force? Okay, and I'll give you one more minute. I'm seeing a couple of people nodding now. You do need to have brackets around those two numbers that are being added. Otherwise, you're simply going to divide by 1 and then add the square of the other. All right, when you calculate the force due to gravity between the moon and the Earth, well, you're still going to use G, mass of the moon, but now it's mass of the Earth over the distance squared. And this time the distance that you're going to use is the distance between the center of the moon and the center of the Earth. So we're going to have G times the mass of the moon this time times the mass of the Earth. Well, times the mass of the moon, just like last time. And then this time times the mass of the Earth. Over, we're just going to have 3.84 times 10 to the 8. And that's the number we square. And again, you're entering it with the exponential notation. And I don't expect everybody to have it yet, but you have it, so I'm just going to write it down. Go ahead.
1.98 times 10 to the 20.
1.98 times 10 to the 20. And I'm going to give everybody a couple of minutes to catch up. But as you do so, I need people to confirm or deny that that's correct. It's correct. So we're questioning the first one. What did you get?
I got 6.4.
Did anybody else get 6.4 times 10 to the 31? You know what I suspect? Yeah, I suspect you forgot to square R. Yeah. We're okay then? Okay. So what's interesting about this, I don't like to just do these questions blindly and get numbers. I like to think about them. What's interesting is even though, look at where the sun is compared to the moon. Even though it's so much further away, and the inverse square law says the force should be a lot less, because of the almost unimaginable mass of the sun, it's hard for you to wrap your head around this number of kilograms. Because of that large mass, the force pulling the moon to the sun is over twice as great as the force pulling the moon to the Earth. But these two forces are both to the right. If I were to go back and amend my diagram here, This is what it looks like approximately. And since forces are vectors and we want to add them to find the total force, if they're in the same direction, we add the numbers. Are you with me on that? That if my puppy Panda is pulling a chew toy to the right with 10 newtons, and my other puppy Scout is pulling the same chew toy to the right with 20 newtons, that's 30 newtons to the right. So F net is going to be equal to the sum of those, 4.3. And I understand that that was rounded, but you can carry more decimals if you feel the need. We're in learning mode here. We're not in exam writing mode. We're going to add this to the 1.98 times 10 to the 20 kilograms and get what I'm going to say is 6.3. Can we live with that? 6.3 times 10 to the 20? And I made a mistake here in what I just wrote. Who can tell me what I've erred in? Zahara? Right. I wrote kilograms and I even said kilograms, but these are forces in newtons. So you get about 6.3 multiplied by 10 to the 20 newtons. All right, let's try another one. Determine the net gravitational force on the middle mass due to the other two. I want to set the stage here. This isn't really an application you would see in the real world, but you need to know the procedure for doing this because when we talk about electric forces next year, it's the same kind of idea. So there will be a force on B due to A. There's a gravitational force on the center force, center mass, due to the mass on the left. Okay. And that can be called the force of gravity on B due to A. And one thing I want to add here, is that if you're asked to find the net force on B, it might help you to imagine that the other masses are glued down. We don't care about where they go or where they are pulled to. We care about where B will move. And B would be forced towards A. Now at the same time, it's a tug of war here. B is pulled towards C. And if I had to guess, I would say that the force of gravity pulling B towards C is going to be greater. Because when I look at the mass of C is over 2 times more massive than A. I know that C is a little further away, but I don't think that extra little distance is enough to really decrease the force. So now, listen very carefully here. Over here in this question, I wrote down how we calculated these two forces. I started off today by saying you need to know how to use Newton's universal law of gravitation, like that. So what I'm asking everybody to do is use this formula, Fg equals G mm over r squared, and I would like you to calculate each of these two forces. Because I'm not writing anything down, I'm going to calculate them up here if you need to follow along. no way that's right. And I immediately see what I did here. So G times M over R squared. Anybody else get 3.4 times 10 to the negative 7 newtons? Okay. Perfect. Let's do the same series of calculations. This time it's 840 and 270. And it's 5 squared. Does anybody else get that number? I hope. And I hope you would agree that this calculation is not a big deal. You know, when it comes to your exam, will there be a question where I ask you, calculate a gravitational force between two masses? Sure. But that's a gimme question, really. So now the question is, what do you do to these two forces? And you can see, by the way, this force here you're going to have to organize your thoughts in some way that doesn't involve a highlighter unless you happen to have a bunch of different highlighters. This force here is this number, and this force here is this number. So if we want to find the net force, let me redraw this maybe a little bit more to scale. Since these two forces are in opposite directions, we're going to subtract them to find the net force. So we're going to have to take this force that's currently on my calculator minus that 3.3794 whatever times 10 to the negative 7. And we get that answer, 2.67 times 10 to the negative 7 newtons to the right. I actually neglected something here in the previous example. We got an answer of 6.3 times 10 to the 20 newtons. There should be a direction on that. You should be saying towards the Earth and the Sun, or to the right in the diagram. But I think it's obvious it's to the right. Here, it's to the right because the force to the right is greater than the force to the left. So my plan is to do one more example with you. And things keep getting bumped, but we have lots of time in the course, and I would rather sacrifice time for quality. So we're going to do one more example, and then I'm going to give you a handout that deals with some extra practice universal gravitation problems that we're going to start working on today. We're going to continue to work on tomorrow, and tomorrow will be the day that I talk about that written response problem. I believe I said that that written response is due Friday. It's not due Friday anymore. I'll let you know tomorrow when it's due. It'll be Monday or Tuesday. Okay. Our exam is definitely not Tuesday of next week. Definitely not Wednesday. Looks like Thursday now. And I think with what we have left after this, Thursday is going to be what we do. Okay. So let's do the last example together here. I know it's been a long haul, but number 3 says determine the magnitude and direction of the net gravitational force on that 45 kilogram mass due to the other masses. What's not given here is the fact that those masses form a right triangle. Okay? So if you want to find the net force on, let's make our lives just a little bit easier and write A, B, C here. Do you happen to have letters on yours? No. Let's just go A, B, C, then we can do some abbreviations. What you want to do is calculate, and please don't calculate it yet, okay? Please, just hang on. You want to calculate the amount of gravitational force on B because of A, and you're going to want to calculate the amount of gravitational force on B because of C, okay? But before you get started, I want to let you know where we're heading with this. When you look at example 1, these two forces that we had to find that were both being applied to the object of interest, to the moon, were in the same direction. And when you add forces that are in the same direction, you know, it's very elementary in nature. You add the numbers, right? In example 2, the two forces that were acting on the object of interest, the center mass, those two forces were in opposite directions, and we've learned that when you add vectors that are in opposite directions, you subtract the numbers. And that's how we got that answer. I'll even just put this up here. That's how we got that answer. So if you want to find the net force acting on B here, you have to calculate those two forces, but then you have to decide how you're going to add them. Like what you're going to do mathematically to find the total. Well, you can't do that until you draw a free body diagram showing the forces acting on B. And B is attracted to A. Imagine A is glued down. B is pulled towards A. B is also attracted to C. So now we're going to be dealing with two forces that are perpendicular to each other. We're going to have to draw the tip-to-tail situation. And I don't consider any of the steps here difficult. Calculating each of these forces is easy. Adding two vectors tip-to-tail is easy.
Excuse the interruption. With grade 10 students, with the last name from K to O, please go to the Learning Commons for retake if you have not had your picture taken or you want it at retake. That's grade 10, K to O. Thank you.
So do me a favor. Let's start with the first step here, which is to calculate how many newtons of force are acting on B due to A and how many newtons of force are acting on B due to C. It's a GMM over R squared calculation. Make sure when you do your calculation that when you divide by R squared, you divide by 0.26 squared. Because we have to use units that are meters because the units in G have meters in them, have standard units. We have to use standard units. Yes? So 1.554 multiplied by 10 to the negative 6 newtons. And, you know, if we want, we can put left so that we can talk about the vector. I don't think you need to necessarily write left. You can see that it's to the left by looking at the diagram. And then what do we have? Same kind of calculation, except this time it's 75 and 45, and we are dividing by 0.42 squared. So 1.276 times 10 to the negative 6 newtons. And looking at the diagram, that is down. And really what it boils down to now, everybody, you know, this is kind of like what I was saying earlier about in math. You take a problem and you make it simpler. We've gone from this really complicated problem to now you having a unit 1 problem where you have to add two vectors that are perpendicular. You draw them tip to tail. And hopefully you remember to draw them. Oh, look at that. I have a nice vector diagram already drawn. Hopefully you remember my advice to draw the horizontal one first. So what we are dealing with here, is, oops, this situation where you have the 1.55 times 10 to the negative 6 newtons. You also have the 1.276 times 10 to the negative 6 newtons. I mean, I wouldn't go so far as to say that the rest is, well, yeah, I would. The rest is easy. The Pythagorean theorem is what you're going to use to find the number of newtons that the net force is, and the angle, which is going to be so many degrees south of west, assuming we're looking on a map, is found using tangent. I think the rest is easy. I don't think it's difficult at all. I would, little point of advice here, I would avoid drawing that triangle on the diagram that's there. Don't do that. You draw that elsewhere. Because I don't want you to confuse that triangle with the triangle that we had in the question showing the positions of the masses. And just before I finish this off, if at some point in this lesson I said charge instead of mass, that's because my head is right now in physics 30. So if I happen to say charge, what I meant is mass. I don't think I did, but I might have. And again, if it's a written response question, I'm going to want to see your work here. But finding a hypotenuse, knowing two legs of a right triangle in grade 11, squared plus squared equals, take square root, and Alex, what do you get for the hypotenuse? Yeah, no problem. And Aoki, have you got the angle? You tell me and I'll tell you if I think it's right. Are you in degrees? So how are you finding the angle? You did tan, didn't you? Yeah. You want to go inverse tan. So what did you get? Can you tell me, Alex, for the hypotenuse?
2.01.
Okay. And I'm going to go under an assumption here that you carried either all of your decimals or a lot of decimals. You carried all the decimals. You kept grabbing them from up top. Okay. Aoki, you let us know when you get an angle. Looking at this, the opposite side is a little shorter, so it's going to be a little bit less than 45, I would guess. What do you get? So let me write out what we have to do here. What you would do is you would say tangent of the angle equals the opposite side over the adjacent side. So we would have tangent of the angle. The opposite side, when we look at our triangle, is the one opposite to this angle is over here, is 1.276 times 10 to the negative 6. I want to just check here. You're using the E thing, right? Over 1.55 times 10 to the negative 6. So you would calculate that. Yeah, okay. Just while we're waiting for an answer here, if I were doing this, it's not that I would cross them out on paper. I probably just wouldn't use them. They're both times 10 to the negative 6. So what do you got now? So I'm going to say 40 degrees. 40 degrees south of west. Any other? How many of you say yes? Good. So this is a bit of a gargantuan question. It can get a little worse in physics 30. But, you know, all of the pieces are real kind of basic. But putting them all together and understanding how everything fits together is the challenging part, I suppose. Okay. So I'm going to give you a handout right now. And there are going to be certain questions on this handout that I want you doing for sure. I'll give the questions to you right now, and then I can end my recording. The focus here on this handout are numbers 12 through 18. This is not for homework. I'm not saying you have to do every one. But when you look at questions 12 through 18, I can show them to you. This is what the handout looks like. There's all kinds of problems where you're calculating forces, weights. But then 12, all of a sudden you're dealing with multiple masses. And that's what we focused on today. So 18, for example, is the only one like example 3. You got to make sure you know how to do 18. All of these other ones are important. So if I said to you, if you said, what should I do for tomorrow? I would say 15 through 18 or 16 through 18. Do 18 and a couple of other ones. But anyway, I'll just leave this up here. You don't have to do them all. So let me hand this out, and we can get to work on that. I know there's not a lot of time left, but when we come in tomorrow, we're just getting to work on this stuff. Okay? Getting lots of practice tomorrow.